confusing. I tried to read some of these early papers after the war to get a feeling for how Hanbury-Brown Twiss interferometry was developed, and it's extremely confusing. It's one Fourier transform after another, basically. Nevertheless, these people who were dealing with a brand new problem brought a lot of new ideas to industry and science, and there was an explosion then of technology after the war in the 1950s and 60s. Hanbury-Brown decided to turn to science. People who had developed radar turned their radar dishes from planes up to the sky to measure what were then called radio stars. They turn out to be galaxies in most cases, but Hanbury-Brown wanted to join this new radio astronomy program. These radio stars were being measured by Amplitude interferometry, Michelson interferometry. And I'll just say a few things about this. I know we all know about the two-slit experiment and stuff like that, but let me just lay some concepts out there so we're all on the same page. For Michelson or amplitude interferometry, which is the kind that we all know about, really I can imagine a point source very far away so that the waves as they come towards my detector down here are plane waves. This is a point source. So these plane waves, as they're impinge upon two slits or two mirrors or two fibers or two telescopes, two of something, okay? The light is then combined behind them on effectively a screen, and as we know, there will be bright and dark fringes where the position of the dark fringes is given by the ratio between the wavelength, which we know, and the separation between the slits or the baseline, which we also know. So the fact that there are these fringes here is no big surprise. You're not really measuring anything. On the other hand, if I have, once again, my point source, I've drawn this green just to keep track, but it's the same wavelength. So if I have this point source over at some angle eta, I get exactly the same pattern, except it's shifted over in sine theta by sine eta. That's fine. So I get exactly the same pattern. I'd like to measure the size of an extended object, not a point source, but an extended object is made out of point sources. So let's just consider two of them. Once again, these are the same wavelength. I just draw them as green and red to keep track. If they are emitting chaotically, which is to say, they're not emitting in phase. A star is not a laser where every point is emitting in phase, but there are random phases. In that case, the intensities of the red point and the green point add. Okay, the intensity. So I get this red signal, which has minima. I get the green signal, which has minima. And the resultant doesn't have dark fringes. It has darker fringes, but not totally black. And that's kind of the point. So if I add these two intensities together, I get a pattern given by this, has some kind of brightness, yeah, sure. And there's some oscillatory behavior as a function of theta. But then there's a prefactor which determines the so-called visibility. So we see fringes, but now they're kind of grayed out. This is a low visibility curve. So what's the interesting thing is, in fact, that visibility, it doesn't depend on theta. It's a constant that depends on the baseline, which we know, the wavelength, which we know, and eta, which is what we're trying to figure out. We're trying to figure out the extent of the star by looking at the visibility as a function of baseline. So we change the baseline, see the visibility, go from very bright fringes to no fringes to bright fringes, and that's how I get a sense of the separation or the size of the object I'm looking for. So this is what one looks for in amplitude interferometry, looking at fringes on between two slits or something like this. And the resolution, the size of the object that I can measure, is indeed given by the wavelength divided by the baseline. So if I want to measure a small source, I need small wavelengths or big baselines, which you kind of knew already. At the heart of this is the fact that the light has to travel unimpeded from the source to the slits or mirrors or fibers or whatever they are, okay? Or any distortion in this light has to be common between these two sources. Also, the light has to travel undistorted from the slits to the screen. That's easier. You're not going through the atmosphere there. Nevertheless, you need phase stability for this to work. That's challenging. First of all, we have turbulence in the atmosphere. Any kind of turbulence leads to an index of refraction change that will slow down the light or something like that. So one could imagine, for example, some kind of turbulent light which slows down the light as it comes to this slit and not that slit, because after all, this is location dependent in the atmosphere. That causes a shift of the pattern. And you could see right away that this will ruin your interferometry signal. You'll get a graying out of the signal, not because it's a large source, but just due to atmospheric disturbances. That's one challenge. Another challenge just comes from this. If I want to measure a small source, I need a large baseline. In principle, you can build the baseline as big as you want, as large as your country is. In practice, that's not so easy. So before the war, Michelson himself was measuring the size of these stars in the optical wavelengths, so visible light. He measured, for example, Betelgeuse, this star. It has a size on the order of 4.8 milliarc seconds, or in radians, I guess it's 10 to the minus 7 seconds. And if we then go through our formula here, we would find that if we use yellow light, so 575 nanometers, we would need a baseline, which, let's see, what's the baseline? The baseline would have to be 10 feet. I love going to a non-American country and using our units, okay? I mean, it's 3 meters, but it's 10 feet, okay? And he was using the Mount Wilson 100-inch telescope. 10 feet is more than 100-inch. So he took this very nice telescope, and he just bolted right on top of it a 10-foot mirror. Actually, I believe it's a 20-foot interferometer. So he just used this nice telescope as something to bolt things to, and this was the interferometer. So the way this worked, this is a little sketch on the right here. You see that there are mirrors here. They can move to the left and right. And the light comes from the star, hits these mirrors, and then some other mirrors, and then it's recombined down at the bottom, hopefully with stable phase relationships. And here's, in fact, a picture of Michelson himself looking through a lens at the fringes on a screen, actually with his eyes. Okay? And what he said as he was doing these measurements is, you know, you can actually see the interference fringes pretty well, even though they sort of fluctuate due to the atmospheric disturbances, and your eye can follow them unless the disturbance from the atmosphere is too great. So you can see the challenge in these measurements already. Nevertheless, he could reliably measure the size of these stars, at least as determined at the time, and so they decided to measure smaller sources and build now a 50-foot, so a little bit more than twice as large as the 20-foot design, to measure stars that were even smaller. However, this failed because it was built out of steel. The steel flexed too much just due to any kind of vibration that ruined the phase coherence between the light that had to recombine at the end. So one wasn't able to measure stars with visible light and Michelson interferometry that were any kind of reasonable size or anything that was interesting. And that was the end of optical interferometry with the Michelson amplitude interferometry, the kind that we all are familiar with, for decades. There was anyway a war, and during this war things changed. As I said, we have this atmospheric turbulence that affects much less radio signals. It affects optical signals a lot, but not so much radio signals. Furthermore, there was the war, which developed the technology of radio signals and radar, and one can live actually with much larger baselines that would be required for the longer wavelengths of radio. So one could try doing this with radio waves as opposed to optical waves due to these advances made during the war. In fact, shortly after the war, there were radio astronomy measurements of two sources published simultaneously in Nature, so all of them in the same journal of Nature that was prearranged, of course. And this was a star, or a source rather, in the constellation Cassiopeia and another one in Cygnus. They all measured exactly the same thing. I mean, the titles are the same as each other. The only thing that changes is the observatory where it was done. The source that was measured in this case was on the scale of 10 to the minus 3 radians or so, and they used radio light 200 megahertz, or about 1.5 meters, so much larger than the optical light. 2 of these measurements were done with Michelson interferometry, just exactly like what we were saying before. So if I want to say what's the baseline that I require, well, if this is the size of my star and I know that my lambda is 1.5 meters, that tells me the baseline had to be like, you know, half a kilometer. So then you use kilometer scale baselines, which you say, oh my God, this is a huge thing, and it is. But one could transmit radio signals very easily, they're only 200 megahertz, over cables. You don't need mirrors or something like that. So that makes it relatively easy. They were able to measure the star. The 3rd measurement was by Hanbury Brown, who got consistent results with the first 2, so they all got the same thing. But this is just a little clip from his paper. As a matter of fact, it's almost the whole paper. These papers are very short. And let me pull out a couple relevant quotes. The first thing was he wanted long baselines. He thought he could even go to baselines on the order of 4 or 5 or 6 or 7 kilometers. He said, however, for baselines that large, this would prove to be difficult. For this reason, an instrument, an interferometer of completely new design was developed for this measurement. And the theory is very involved, and it will be given in detail elsewhere. Now, if I tried to publish this today and said, you know, I got this detector which no one ever heard of before, and I'll tell you how it works later, but believe my results, you can forget about it. But it seemed to work, and in fact, he did describe this measurement, but only 2 years later. Okay. So this is the paper from 2 years later. It's a real classic in Philosophical Magazine. And what he was able to prove was that you could go to very, very long baselines and you'd be unaffected by atmospheric turbulence using this new technique of intensity interferometry, different than Michelson interferometry or amplitude interferometry. And let me say a little bit about how this works. It's a simpler case. In this case, I have my source, which is way up that way, I guess, and we look at a very narrow bandwidth signal, which is to say a very small range of frequencies that come in. So I have a star or a source somewhere in the sky, just like my red and green things before, that's emitting with a very small bandwidth and noise. Well, you know what happens when you have a small bandwidth. You start to get beating features, okay? Just like if I have 500 hertz or something like this on a piano and 551 hertz, I'll get 1 hertz frequency beatings. And if it's noisy, well, it won't be totally beats, but I'll anyway get intensity fluctuations on the scale of 1 over the bandwidth. That's much larger than the frequency of the light itself. I bring this into some kind of receiver, some kind of radio receiver, and into what you could call an intensity detector. Intensity detector just means how loud is the signal. And you could listen to it like that. Okay, so you didn't even have to pay attention to what's the phase of the electric field as it oscillates, just how loud is it? What about the sound oscillations? So yes, the phase information is discarded. This was a relatively difficult design to build and to explain. Nevertheless, it was rather simple in implementation. So of course we have an identical receiver right here. The same light hits this receiver. Naturally, there's a so-called optical path delay just due to trivial geometry, and that is accounted for by a delay line here. I'm going to talk a little bit at the end about that delay line, but all it does is take into account that this light has to travel a little further. So I have this light coming from my green point source in the sky hitting my 2 receivers. Oops. And I also have that other red point that's at a slightly different angle, eta, like we talked about before. In this case, you have a different set of fluctuations. They have the same scale, 1 over the bandwidth of the signal that you're looking at, but you have different fluctuations. And the theory is, if you work it out, and it's actually pretty straightforward, that the correlations between the telescopes, the intensity correlations, the loudness correlations, nothing to do with the phase of the electric field, will be correlated. And in fact, these were measured, the signal was measured on paper strips as they went through a recorder, at least early on. These 2 signals were recorded. here, and they were also correlated with a special circuit designed by Hanbury Brown that measured the product, really, the multiplication of these two signals and recorded them with a recorder. Okay.
Your source is, you're getting sign from the same source in both detectors.
Yes. So the way I've drawn it here is that there are 2-point sources, just to make it clear. So that's with analogy to before.
Okay.
And, you know, naturally, there's an infinite number of point sources in any star, but I just wanted to make the point with 2 of them. And this technique could measure the angular separation between those 2 sources. So if I have an infinite number, I'm measuring basically, you know, the range. Well, why is the amplitude different and the fluctuations different between the red and the green? That was... Right. Well, it's just like before. Remember how before on the screen there was a small shift when I was looking at the green one because it was off at some angle eta, which is what I wanted to measure? There's a shift in time here as well. So it's the exact same reason. So you don't, the signal coming to the right hand, I don't know if I called it A and B, the signal coming here, the loudness fluctuations here are not identical to the loudness fluctuations here, basically because of a small optical path difference between red and green. I've exaggerated it on this graph to make it clear, but there will be a correlation between the signal here and here, and that's kind of the whole point, but they won't be identical. Unless these 2 detectors are at the same location, in which case you get a full correlation, and that is what is seen. Does that answer your question?
Yes.
Okay. It's not trivial, and you know, very few people have done correlations or HBT in both particle physics and astronomy. I think I might be the only one. And it's very interesting to think of this as a time correlation. And I'll show this a little later. As long as I've stopped, are there any questions? I don't know, from online or anything. Looks like not. Anyone else? Feel free to ask. Good. So what's measured then is this normalized correlation. It's the average, the time average, of the product of the signal divided by the product of the averages of the 2 signals. And what that corresponds to is, in fact, the geometry of the star. So here's one of the first measurements of this so-called correlation coefficient as a function of baseline measured in units of the wavelength of the light. For one source, I don't even remember, okay, it looks like it's in Cygnus. And in fact, what is seen is the correlation coefficient does depend on baseline. This star has hard edges. It's basically like a disk, so you get what might correspond to diffraction fringes as you go out. And this then is the correlation corresponding to the extended source of this star or of this celestial object. It's brilliant that this works. Absolutely brilliant. Let's see. So this HBT interferometer, this one is using radio signals. That contributed to a growing catalog of sources, about 100 stars, actually a little bit less, in the 50s and 60s. It was, you know, with Michelson interferometry, it started with optical wavelength, very short wavelengths, and then it was applied to the radio signal. It was rather a natural suggestion to say, hey, listen, intensity interferometry, this new type of interferometry, works for radio signals. Maybe we can apply it to optical signals, okay? That was written at the very end of Hanbury Brown's brilliant paper from 1954. That caused all sorts of problems because, you know, the intensity interferometer removes the issue with turbulence in the atmosphere for reasons I could talk about if we want to, and that was why Michelson was failing. So it would be interesting to apply intensity interferometry to optical wavelengths. That started off a firestorm of controversy. This is a workshop on intensity interferometry in subatomic and astrophysical systems. Almost everyone here did subatomic intensity interferometry. I happened to be there, and so did Hanbury Brown. It was a tremendous honor to meet this guy, I have to say. And this was in Sicily a number of years ago. He submitted a one-sentence abstract for his talk, which was, of course, the keynote talk. He said, this talk will give a brief history of the early development of intensity interferometry and its subsequent battle against common sense. And that's for sure. The literature is hot with this. Early on, when Hanbury Brown was talking about radio waves, he developed the formalism, was able to prove that this instrument should work, was able to do it theoretically and experimentally. Importantly, there is no H in HBT. There is no Planck's constant. It's not a quantum effect. On the other hand, particle physicists or the early modern quantum physicists said, oh, if you're talking about optical wavelengths, we have to think in terms of photons. And one thing you find in Dirac's textbook, I went and looked it up at our library, is a statement that every photon, everything's about the two-slit experiment at the end, every photon interferes only with itself. Interference between two different photons never occurs, which is a nonsense statement. It's not even wrong. It's not right and it's not wrong. It doesn't make any sense, and I'll try to say something about that. Hanbury Brown, pointed out, he tried to point out that this was wrong and said that the existence of a correlation between photons has been denied by, modern physicists, and the error appears to have arisen because of a too literal reliance on the corpuscular picture of light. In other words, the particle picture of light. Now, Dirac was a Nobel Prize winning physicist. Hanbury Brown was an engineer who didn't have a PhD in anything, certainly not physics, and he didn't have a Nobel Prize. This was sort of an unfair battle. As Hanbury Brown tried to explain what he was doing, it got worse and worse, I have to say, if I read the literature. And it required other physicists, for example, Purcell, who did also win the Nobel Prize, who pointed out in a very short letter that the Brown-Twiss effect, as he called it, far from requiring a revision of quantum mechanics, is an instructive illustration of its elementary principles. And that turns out to be totally true. Hanbury Brown pointed out that, we see this correlation in radio wavelengths. It is to be expected, at least on classical theory, it's just an electromagnetic wave. There are radio photons too, if you like to think of it that way, at optical wavelengths. And this was somehow overlooked as if there was a quantum and a classical realm that was distinct from each other. Importantly, what he points out, and this is what the whole HBT and quantum optics field is based on, and this is why Purcell made this statement, is that you should not think of photons as particles that travel. We draw them that way all the time with Feynman diagrams, but it's not true. It is more useful and more correct to think of a photon as an event when electromagnetic radiation is emitted or detected. In between, it is purely a wave. Photons do not travel. Okay? An important concept which is actually hard to fully grasp. This is an example of somebody coming from entirely outside the field, not in physics. He's an engineer who developed radar, thinking about how to measure sizes and positions with radio waves, entering a brand new field of astronomy and bringing a brand new idea to it. It eventually led to quantum optics, as I'll say in a moment. What he measured early on was the correlation between radio waves, for example, even just using the crudest equipment possible. He said, listen, if I don't need the phase of the radiation, then I don't need very good mirrors. All I need to do is collect radio waves. So the first measurement, which I think was, done of Sirius, used simply searchlights from the war days to collect radio waves, and he measured the correlation between them. This was the first measurement that he had done, and was able to see this correlation which correspond to the size of the star. This is the correlation expected for Sirius, and these are the correlations he'd measured. And you can see he only separated these things by like 14 meters. Okay, so it was a very crude measurement, just to prove that it worked. Nevertheless, this crude measurement was the beginnings of quantum optics. Roy Glauber, of course, in 2005 won the Nobel Prize for his work and development in quantum optics. And he pointed out that this statement by Dirac that each photon interferes with itself and an interference between two photons never occurs, a classic textbook in the 1930s on quantum mechanics. He says, forgive me, this is quantum mechanical scripture, but it is also complete nonsense. And his talk, I just sort of did a screenshot of one of his slides. You know, he talks a lot about this Hanbury, Brown, and Twiss measurement. And you could even say that one subtitle for his lecture really ought to be why Hanbury Brown should have won the Nobel Prize as well. Okay. So, having proven that intensity interferometry works for optical sources and wanting long baselines, Hanbury Brown traveled to Australia to build an observatory. It uses two telescopes that measure the intensity fluctuations of visible light. So they look like this. All they are is mirrors that catch as much light as possible, shine it up onto a photomultiplier tube, which, as you've ever used one of these things, just measures the brightness of light that comes in, not the electromagnetic phase. That's gone. Okay? So it's equivalent to listening to a signal in here like this, if you've ever looked on an oscilloscope. That's these two things which sit on a track so the baseline can be varied. Let's see. And we can see that they each have a cable that just transmits the analog signal from the photomultiplier tube to a central shack where this special circuit multiplied the two signals together and recorded the correlation. Okay. This led to, again, a growing catalog now of optical sources in the 50s and 60s and into the early 70s. And in the mid-70s or early 70s, this type of interferometry was also ended for two reasons. One is it needed very bright stars, and you kind of used up all the stars. The other one is that Michelson interferometry, which is much easier to understand and, in fact, easier to implement experimentally, the issues corresponding to atmospheric interference and phase stability were overcome technologically, so most people started doing Michelson interferometry, and intensity interferometry for astrophysical sources kind of ended. Nevertheless, we still see remnants of this today, and in fact, a rebirth of this today. This is the RIC Collider on Long Island. It's about 2.4 miles in circumference, so I don't know, 4 probably kilometers in circumference, finished in 2000 on Long Island, New York. And how did we get here? Why did I jump from a radio astronomy or an optical astronomy interferometer in the 1960s to something that we measure in the year 2000? Well, to answer that, I have to go back to the 1960s. So this is Hanbury Brown's observatory in 1963. At about that time, particle physics was being developed, and the antiproton had recently been discovered. There's a classic paper by Goldhaber, Lee, and Pais, GGLP, which took a look at the annihilation of protons and antiprotons. When they annihilate, the proton and antiproton disappear, and you end up getting an even number of pions. 6 pions, 8 pions, I think sometimes 10 pions. And let's see, what did their data look like? What they did is they looked at all the pairs of the pions and what was their angular distribution of emission. You're not surprised with only having 4 or 6 or 8 pions that most of the time they came back to back, just due to momentum conservation. That makes sense. On the other hand, there's more than just 2 particles, so some of them don't come back to back, and one can make a distribution shown here. So this is the cosine of the opening angle. Most of them are emitted at 180 degrees due to momentum conservation, like I said. And they broke it up and took a look at pi minus, and pi plus, which is to say like sign pairs, and unlike sign pairs. And they said, you know, these distributions look a little different. They said, all right, let's run a statistical model where all I'm doing, it's like Fermi's golden rule with phase space constraints, is conserving momentum. And they said, this is what I would expect from this distribution, given the mass of the proton and the mass of the pion, et cetera. And they said, you know, this distribution seems to describe the opposite sign pair pions much better than the like sign pair pions. And he said, okay, well, look, one thing we know is that like sign pions are identical to each other. I mean, if I have 2 pi minuses, that is 2 identical particles. The wave function that describes them has to be symmetrized. And that's not included in a simple Fermi's golden rule model. Let's build in this symmetrization. When they did that, we got the red curves. This changed everything. They didn't know that at the time, but this changed everything. And if I had a student who brought me this data and said, this is going to change everything, I say, that sounds great. Go get more data. I mean, you've got to be kidding me. Look at these error bars. But they realized, or they intuited, or they made a really good guess that this was important. These distributions were, in fact, different due to the symmetrization effects. Okay, that's fine. Clearly, there's a difference, even though a small one. The effect of those symmetrization effects, the difference between the red and the blue curves, not surprisingly, depends on the size of the source that these pions were coming from. That makes sense. They assumed a 3/4 Fermi source about the size of a proton. That makes sense for proton-antiproton annihilation. However, one can measure this difference and start getting a sense of the size of the source, even not for proton-antiproton. For particle physics, this HBT, or actually it was known as the GGLP effect, was known, was understood, was kind of a cute little footnote. It was sometimes important when measuring the mass of the W boson for electroweak physics, but otherwise it was kind of a footnote. However, in heavy ion physics, it plays a very prominent role, and I want to talk a little bit about that. Heavy ion physics often looks a lot like particle physics. You take a look from an airplane and you could take a picture of the detector. All the detectors look more or less solenoidal as they go about the beam direction, which are underground. I even don't know if this is from the LHC or from RIC. They all look the same. The detectors look the same. The only difference is people in Europe are a little bit smaller than the people in the US. But, you know, so it's really just a matter of scale, okay? Both facilities measure proton-proton collisions and nucleus-nucleus collisions. They both do that. They do it at somewhat different energies, but they're very similar. To tell the difference between these facilities, we look at the name. Naturally, C stands for collider. But for RIC, H stands for heavy, which is to say the focus of the physics program is on nucleus-nucleus collisions. The proton-proton program is parasitic. In other words, it came along for the ride, an important part of the ride, but that was not the focus of the facility. On the other hand, at the LHC, the H stands for hadron, which means proton in this case. So the proton-proton program was what was important, and the nucleus program was parasitic, sort of came along for the ride. The LHC was not built for nucleus collisions. In fact, here, the H might as well just be called Higgs. So in terms of particle physics and nuclear physics, the difference really is in scale. In particular, the strong force between colored objects, given by the theory of quantum chromodynamics, is the least understood of all the forces in nature. Therefore, it's the one that we're interested in. It has a running coupling constant, just like electroweak has a running coupling constant, but here the running is very strong, and it opposite to the electromagnetic effect, for very small distances, large Q squared, large momentum transfer, it's a very weak coupling, and at large distances or small momentum transfer, it's a strong coupling. And the reason behind this is because unlike electromagnetic case where photons do not couple to photons, gluons do couple to gluons. That makes it tremendously more difficult. In particle physics, you want the highest energy possible. Why? Because you want to make heavy things, supersymmetric, whatever, I don't know. You're trying to make very interesting particles. Furthermore, you really don't want the complications of quantum chromodynamics. You want a very simple system, small, proton-proton, not nucleus-nucleus, high energy to make massive particles, and high energy to ignore QCD as much as possible. The focus here is on the particles. In heavy ion physics, the focus is on the interaction, Okay, so we come down to low Q squared. QCD has a scale, okay? Protons are 1 Fermi big, they're not 1 centimeter big. They have a mass of 1 GeV, not 500 keV or something like that. That's a fundamental scale of a fundamental theory that we want to understand. So we focus at a given energy range. That's why QCD studies at the LHC are not really important. They're important at RIC. In this case, there is an optimal range. Bigger is better. We want to make a massive system, not a very small system, when we want to measure low Q behavior. Basically, the primary and signature phenomenon of QCD is that of confinement, the fact that colored objects are always trapped inside protons and neutrons. In fact, you know, when we think of CERN and the Higgs boson, it's often said that the Higgs is what gives the universe its mass. Okay, clearly we're talking about the visible universe because who knows about the dark sector. But even for the visible universe, this is nowhere near true. Most of the mass, almost all of the mass, come from baryons, protons and neutrons. And 96% of a proton's mass does not come from the Higgs. It comes from the complex interactions between quarks inside the hadrons, from low Q squared QCD, which we don't understand at all. It just fits better on a t-shirt to say the Higgs boson gives everything mass, but it's only 4% true. Okay, so that's why QCD is interesting to us. In nuclear physics, in heavy ion physics, space-time is crucial. We start with a small collision, which then turns into what we think is a quark-gluon plasma, colored objects interacting in a plasma. It expands in a non-trivial way, and we wind up with this picture in our detector, many billions of collisions. It's a lot like the early universe, which started off with beginning lumpiness, and it also started off as a quark-gluon plasma, as a matter of fact, and then finally ended up with structure that we see today. And our goal is to sort of play back the Big Bang. In heavy ion physics, we're looking at the little bang, and the tool that we use is three-dimensional viscous hydrodynamics. That's one of the main tools, which takes a lumpy initial condition, evolves it as a function of time, and this evolution is highly non-trivial. Now, when I make measurements of these collisions, I only measure the momentum and energy of the particles, not the space-time features. Meanwhile, I just told you space-time is crucial. So, what can I do? In the 1970s, shortly after the GGLP effect was discovered, Edward Shuryak and other physicists, most of them Russians as a matter of fact, realized that there was a deep connection between GGLP and HBT effects, the one that was used astronomically. What they said was, listen, let's imagine I have some sort of source which is on the size of a nucleus, 5 times 10 to the minus 15 meters. Can I measure such a small source with detectors that are on a scale of 1 meter, 15 orders of magnitude bigger? And the answer is yes. Once again, we're going to think of 2-point sources, X1 and X2, which emit pions. Most of the particles created are pions, and they're measured at detectors R1 and R2 with momentum P1 and P2. The wave function corresponding to this process is just going to be the creation amplitude of particle 1, the creation amplitude of particle 2, and then the wave, let's say it's plane waves coming from the source to the detector. If it's not plane waves, we'll put Coulomb corrections in later. That's not really the point here. One thing we know, however, we're measuring identical particles, therefore we have to also take into account this process where particle 1 comes from position 2 and particle 2 comes from position 1. They lead to identical outcomes from these 2-point sources, so one has to symmetrize the wave function, swapping some of the 1s for 2s here, and then probably adding them and normalizing it by 1 over root 2. Very nice. Now, as an experimentalist, I measure probabilities. I can tell you the probability that something's going to happen, but I don't measure wave functions. So the probability, of course, is the wave function squared. And when you square this, we find we get the probability for making one of those particles times the probability for making another one of those particles times something that has a cross term in it. And I shouldn't have written this in complex form. It's just the real part of this. So it's the cosine. So sorry about that. But the point is, I measure this probability for measuring the two particles. I measure these probabilities for measuring the one particles. I measure the momentum difference between my pions. What I want to measure is how far separated are x1 and x2. And then, of course, I have an infinite number, so I'm measuring a distribution. I just wanted to make the simple point here that I can measure this separation with these 1 meter scale detectors. What is formed is, in fact, a correlation function. This looks a lot like Hanbury-Brown's correlation. It's the probability of measuring two particles divided by the individual probabilities of measuring them separately. And this then is related, I told you this was a cosine, to the transform of the source. So what I measure, not in time now, but in relative momentum, P1 minus P2, is a correlation function that dies off at large relative momentum. And the width of that correlation function is 1 over the size of the source. Okay. That is fantastic. From those humble beginnings by Shuriak, this field of femtoscopy, measuring things at femtoscopic scale, was developed by a series of brilliant physicists over the past, 40 years, really. And this dominated the new field of heavy ion collisions. So the correlation function is related to the separation distribution. The separation distribution is just a convolution of the emission probability with itself. In other words, it's just the distribution of separation of sources. That's all it is. For an experimentalist, what that means is if I measure one particle with some momentum, they curve in our magnetic field, so I can measure the momentum. What's the probability to measure a second particle at a similar momentum? More to the point, what's the extra probability to measure the yellow particle given the fact that I've measured the purple particle, the conditional probability? That is what gives me the correlation function and access to the separation distribution, the geometric scale of the source. Unlike astrophysics, where we're really only looking at photons, in particle physics and heavy ion physics, we have a large number. So we have pions and kaons and lambdas and protons and whatever else, cascades, and we can measure the correlations between all of them. It's not so simple as Fourier transforms for all cases, but it is understood. And we can measure these correlations and understand them very well in terms of the underlying geometry. They give us a comprehensive picture of the geometry of a subatomic source. Just to sort of set the scale and show that this works, this is the simple 2-pion correlation function for 3 different systems. For proton-proton collisions, I get a wide correlation function corresponding to a 1 Fermi source. It was very common to measure deuteron-gold collisions at RIC, where I expect something like a 2 Fermi source, and indeed the correlation function is more narrow. And as I go to gold-gold collisions, I measure even a more narrow correlation corresponding to a larger source. It goes beyond just overall size. I just wanted to show that. But we also measure time scale. It's hugely important for this dynamic system, which only lasts about as long as 10 times as, well, about as long as light to transverse a gold nucleus. Lasts a short time. Also, shape matters, not just size and time scale, but shape. Most of our collisions are not head-on collisions, but peripheral collisions. And you can see this overlap zone has the shape of, well, an American football anyway. And this is hugely important in heavy ion physics, as this anisotropic QGP tends to expand preferentially along the short axis. And this evolution is something that we really need to understand if we want to play back to movie and understand the QGP. Not only does size and time scale and shape matter, but also the substructure of the QGP. This is a blast wave sort of picture. And really, these arrows, clearly they have different directions, but also they have a substructure, which we can understand through femtoscopy, 2-particle intensity interferometry. And this intensity interferometry is the only way to measure space-time in nuclear collisions. Let me just say something about it quickly, something really important and really almost trivial. What is a nucleus-nucleus collision? Is it really just 200 proton-proton collisions that happen to occur near to each other? That could be. Here was the other collision happening, or the nucleus coming up. Here are individual proton-proton collisions that happen nearby. They'll emit their particles. If there's no interaction, if there's no system being made, then forget about talking about a new phase of matter. You don't have matter at all. You need a large system. In this scenario, the size of the source would be this whole size here, whether I'm measuring particles going that way or that way or that way. They all come from all over. On the other hand, in our hydrodynamic blast picture, the particles going to the right are coming really from the right-hand side of the source, and those coming from the left are going to the left-hand side. So if I take two detectors, that's these little eyeballs, and let's say I'm taking a look at the bottom right. Well, the pions coming here come from this region of the source, and one can do calculations. How big is that region? What's its shape, etc., and measure that. The upper right eyeball is going to measure faster particles. Not surprisingly, given the blast structure, they're coming more from the edge and a smaller part of the source. Furthermore, not just slow and fast particles, but heavy and light particles will come from different regions of the source. And you can make a rather easy prediction of how the source size should depend on momentum. Here, it doesn't depend on momentum at all. Here, there's a very well-defined dependence, and in fact, it is what's seen. This is now the overall size of the source as a function of the momentum of the particles. It follows a very trivial scaling law, which you would expect from a blast scenario. That's step zero, if you want to talk about quark law and plasma, is like, is it a system or not? And you can only tell that with HBT. Furthermore, we expect the kaons to come more from the edge in this picture, and I won't go into details except to say you can correlate pions and kaons in femtoscopy and confirm that this is indeed the case. You can get down to small structures. Let's see, I think we started a little late, and I would like to get to something else, if I can find my mouse. I'm going to jump to the third part of the talk to say that we can measure the time scale, we can measure the size, we can measure the shape, we can measure the substructure with femtoscopy. I skipped over a lot of stuff now, but I want to come full scale. I told you about the HBT in the astronomy sector, and then I told you a little bit about what was done when we brought this to the femtoscopic sector. I want to spend just a little bit of time telling you how some of us are bringing back intensity interferometry. When we did subatomic physics at CERN and at Richt, a lot of technology was developed, and this could be brought back to the astrophysical case. In particular, remember HBT. There was some sort of connection between the telescopes and some kind of central correlator to measure the correlation as a function of time. You know, these days, we don't really need a central correlator that measures it at the same time. We could take the output of a photomultiplier tube, and really all this is a photomultiplier tube, okay? Digitize it, stream it to fast storage at, let's say, 250 megahertz, and just record the signal. You need a lot of disk, but you know, disk is cheap. You could do this for one telescope, for the other telescope, and you could correlate them tomorrow, which is in fact what we do. We correlate them the next day. Now, these things can be as far apart as you want. You don't need some kind of cables going to a special circuit. And in fact, this is what we're doing today. This is the Veritas collaboration, which I'm now a member of. Veritas is made to measure Cherenkov radiation from cosmic rays. What that means is you look at a dark patch of sky, a cosmic ray enters the atmosphere, makes Cherenkov radiation, and this thing measures flashes of light, and maybe you can get a picture of far-off galaxies. I don't know, because that's not what I do. The main thing is the Veritas collaboration cannot do this when the moon is out, because they need a dark sky. So for 1 week out of the month, they don't measure. And we said, well, we can use that detector system even when the moon is out. HBT is relatively unaffected by low levels of ambient light. So that's what we do. We're a parasitic program. What we do is we say, well, we have now pairs of telescopes. Remember, we need 2 of them. Here we have 6 pairs, all with different baselines. And each telescope is an independent station. We take the signal and store it right here next to the telescope, and we correlate them the next day digitally. Okay? Now, these are the sorts of signals. This is just basically, if you hook up a photomultiplier tube to an oscilloscope, you would see signals that look like this, just noise. Okay? I measure the noise from one telescope, which is blue, the noise from the second telescope, which is red, and I'll correlate them tomorrow. The difference between Hanbury Brown and between this new system is shown here. Obviously, this is simpler. There's no correlator circuit. We do this the next day. There's no delay line either, so I'll mention something about that. I do want to say that we store in 1 hour's observation almost 4 terabytes of data. So it's a tremendous amount of data, but you can do that today. The difference here we have a delay line. Why? Well, because the light coming to this telescope from all the points in the star has to travel a little further than the light coming from this part of the telescope. So if you want to measure the correlation, you have to account for that optical path delay with an electronic delay. That makes sense. We don't do that here because it's fine if there's a delay. This is now the product of these two, the convolution of these two signals. Over time, we do offline digital convolution, and this now is what we call a correlelogram. This was just presented by Jonathan Davis for Veritas at the AAS meeting. This shows us the time into the observation, so this is a 2-hour observation, and this is the relative time between our signals. This is a small effect. This is a part per million effect. Nevertheless, you can see it. You can see that this delay changes as a function of time as the star goes across the sky. No surprise there, but it is so cool to see that. Okay? We don't have to adjust with some kind of wire or something like that Hanbury Brown did. When we align frame by frame, minute by minute for this delay, we just do this with the computer program, no big deal, and overlay the distributions, we can measure correlation functions as a function of relative time here. We're back to astronomy. And you can see that the magnitude of the correlation depends on which telescope pairs I'm using, T1, T3, T1, T4, because they all have different baselines. Okay? This is now the first results from Veritas published in 2000 in Nature magazine. And if we plot now the strength of these correlations as a function of baseline, you see that they form a very nice, what we call visibility curve at a part per billion or part per million, 10 to the minus 6. And we can extract the sizes of these two stars, Eta Orion and Beta Canis Major in this case. They agree with previous measurements. So this is a proof of principle measurement, but it's huge. It's the first digital SII ever done. In fact, it's the first stellar intensity interferometry done for decades. Okay? So this is important. This is now bringing this to a new level, and we can bring this to non-round stars. Let me wrap up. I've given this talk in 3 parts. I talked a lot actually about the insight from radar development during World War II, giving, this brought new people into a new range of scientific enterprise, led to new ideas. A newcomer often brings new approach to a field. I told you that when it was applied to optical wavelength, this actually gave birth to quantum optics, something hugely important today, and a huge field in modern physics in general, and to quantum mechanics. In the subatomic realm, I told you there was a curious effect, the GG-LP effect, that turned out to be closely related, not trivially related, but closely related to the Hanbury-Brown Twiss effect. And the lesson there is pay attention to even small effects in the data. You pull out something that really changes everything. This grew to be hugely important in high-energy nuclear physics, where we call it femtoscopy, and we can extract the space-time dynamics of the system, of the quark-gluon plasma. And then I told you how, using what we've learned now in subatomic physics and the technology we developed, we're bringing this, full circle, so to say, to revive Hanbury Brown's dream. He actually had this dream. He pointed out that, you know, if you could separate and record with very high speed, he was still talking about a paper strip, the fluctuations in one telescope in England and one in the United States, then you could correlate them in Paris the next day. It was just sort of a thought experiment. I would love for him to still be alive today to see that we're actually doing this. And once again, you know, bringing now nuclear physics and particle physics technology, a newcomer brings a new approach to a new field. Let me just end with a statement to the students, don't lose heart. Hanbury Brown, I told you, his career was interrupted by the radar development of World War II. He was the chair of the physics department and astronomy department. He never got a PhD ever. I mean, he was the professor for students who got a PhD, but he only got an honorary one from Sydney after he retired. So there, you know, there's always hope to make a contribution. That's all. You probably want this.
Maybe the camera can find me, I think. So thank you so much for a very exciting seminar. I presume there are questions here. Otherwise, I can ask the people outside for questions. Let's give you the opportunity. Yes.
So in your interferometer, I mean, to measure data from stars, would you have interference from all the stars? It's a question from a curious.
Sure. So the question was, you know, when I'm taking a look at two stars, here, maybe put it up here. When I take a look at two stars, isn't there light from other stars that are feeding in? Here's a question. I mean, if I look up at the sky, I mean, light's coming from everywhere. Why doesn't it look just gray, right? Just in general, forget about interference. Well, the point is because you focus. These telescopes are focused. Those are not flat mirrors. Of course, they're curved. And for that reason, you're looking at a particular star. You really have a clear image of one star. So if there's any collinear light, like a star like exactly right next to it, you'll see both, but they got to be right on top of each other. If there's moonlight from the atmosphere scattering in moisture in the atmosphere, that will affect you. But we do this in the desert, we do it very high up, we do it during the dry season, and that's not much of a problem. So no, the interference from other stars, it's not relevant. The light from another star, the light from the star we're looking at will bounce off the mirror and right into the photomultiplier tube. The light from other stars will hit the mirror and go over there. Yeah, it's a focusing telescope.
Does the focus need some information from the star, like how far it is or something?
You don't need to know how far it is. All you need to do is point the telescope at the star itself. So the locations of the stars are very well known, and we have servo motors which track the star across the sky, which is so cool to see, I have to say. I'm a nuclear guy, so I go out there and I watch these things track. It's gorgeous. And, you know, sometimes you have to adjust in case the tracking gets a little off, but it's very easy, actually, to point a telescope at a star. Yeah.
Okay, another question?
I can repeat the question.
Okay.
Would you please comment a little bit more on the size of the detectors? I mean, spatial separation between the detectors.
Oh.
It seems to me, once we are measuring the coloration between intensities, we don't need necessary huge spatial separation as you show in the picture, right? But then, because there's other measurements about this, for instance, Einstein gravity telescope. So they use this very long baseline measurements. So it seems to me they're also measuring the coloration of intensities, except that they have a huge spatial separation.
Okay, so let me see if I can say something. Yeah, I'll try to repeat, but let me put it up here. So, I mean, we could take a look at the astronomy case or else the subatomic case, but I'll talk about the astronomy case. I mean, this separation, which is on the order of hundreds of meters or so, is about right to measure stars of a few milliarc seconds. So here we have stars of a little bit less than milliarc seconds. What you need to see, the correlation at 0 projected baseline is always maximal, and I think we were talking about that before. You need to see the correlation vanish. So The size of the baseline you need depends on the size of the star you're measuring and the wavelength of the light. Then you were asking something about the Einstein telescope.
So I think this already answered.
Okay.
But can we show more explicitly, because you showed that expression for this HBT coloration. So there's this moments and spatial separation. So where is the size of the detector?
Okay. The size of the detector, like of each individual telescope?
Yeah, because I can't remember if those impressions you only have the spatial coordinates of the source and then the momentum.
Okay, we need to be clear. We're going to talk about the astronomical realm, in which case we're measuring time correlations as a function of separation, or we're going to talk about the subatomic realm, where we're looking at momentum correlations, because they're different. So which one would you like to talk about?
I see. I probably confused.
Yeah, that's a common point.
Yeah,
You
I
know,
mean-
to confuse time correlation with momentum correlation. One HBT is time.
Right.
He
I mean-
mentioned that, but you know, maybe
Yeah.
it's not.
In subatomic physics, we often say, oh, we're doing HBT, we're doing HBT. And the reason we say that is because we don't really know what we're talking about very often. I mean, the connection is there, but it's certainly not trivial. Yeah, so you kind of have to decide which one we're talking about. In terms of the size of the detector, like the size of each one of the telescopes, that doesn't really come in a meaningful way. That's not important. What's important is how far separated they are.
Yeah. Actually, I remember, Mike, you probably read also in Hanbury Brown's book, that he was saying that he was collecting light as if he was collecting rain in a bucket.
Yeah,
The
but-
shape and size didn't matter at all.
Well, it matters a little bit.
Yeah.
But yes, I mean, basically he saw them as photon buckets. The bigger the better is what he was thinking.
Yeah, but you know, it doesn't matter the shape or how, he mentioned that how well mirror, the quality of the mirrors, it didn't matter.
Right.
Right. Excellent. So let me see if is there any another question? Okay, go ahead, Julia.
So I would like to ask you if you can talk a little bit about the problems that you said when you were talking about the atmosphere. And then I have another question. I will just give it.
Okay. So you wanted, so now we're going to go back. Where are we going here? Let's go, let me see if I can help here. So you were asking about the problems in the atmosphere.
Yeah. I
Um,
was curious about that.
Sure. So with Michelson interferometry, I'm going to go back here. With Michelson interferometry, the real problem was if you have turbulence in the atmosphere in front of one of the mirrors or telescopes or whatever it is, that will already lead to a shift in the pattern just because the light was slowed down here before getting, just due to these atmospheric effects. So I'll get smearing of my fringes and the visibility will go down. That will affect my measurement. Now, if I have very long baselines, it's not, how would I like to say that? If I have very long wavelengths, the atmospheric effects are not as important because I really need to maintain the phase stability to within, let's say, order of a wavelength. So if I have very long wavelengths, this is less important. And the thing is, with intensity interferometry, I showed you these pictures of intensity fluctuations. Let me do this right here. I guess I can do it right here. The wavelength of the light is very short, but the relevant thing that you're correlating are the intensity fluctuations, and that's much longer. Let's see if I can put, I think there's a, right here. That's much longer. If we take a look at a narrow bandwidth of the signal, which is to say a very small region of selection in frequency, the relevant oscillations are much longer and therefore much less affected by atmospheric disturbances, by the slowing down of the light. Does that answer your question? Or?
I think so. You have talked about, I think to answer the question, I don't know if in some points of the presentation you said about this problem, and you said that if anyone wants to ask this,
Oh, yeah.
but I think it's answered. But
Ah, yes, uh-huh.
Like, it could be a noise in this narrow detection, or I don't know. Can you explain again why you see this like this?
Sure. Let me see if I can get to the part where that might be helpful. So this is, you're asking about this statement, I think. Right. So we often think of, if I have a very low intensity light bulb or something like this, I can tell whether I've emitted a photon by measuring, voltage fluctuations or something in my LED or my light bulb. And I can also tell when I measured a photon. Now you could say what happened was the photon was emitted here and then it just traveled over here to my detector. That's a natural way to think of it because, hey, it has momentum, it has energy, and even momentum's a vector. That's probably, I just think of it like a particle, but it's not a particle. This photon was an event. It happened. I don't even like to talk about it as an object. This was an event. This happened sometime. Later on, something else happened. There's a relation between them, but they're not the same event. It's certainly not a particle. What happened was a wave phenomenon, and we know, we kind of know this, but we don't think about it the right way. What happened in between was a wave phenomenon. That's what traveled. And the probability to measure a photon at any given place or every given momentum is the square of that wave. We know that, but we kind of forget that it's wave dynamics which affects the propagation, and this wave dynamics is what leads to the interference. So this idea that photons don't interfere with other photons don't interfere with anything. It's an event. It just happened. That's what Hanbury-Brown meant, and that's kind of what I was also trying to say. Does that help? Is there?
Yes, and there is any noise related to this kind of seeing the photon as an event? Because I don't know if I can explain well, but I worked with this radio frequency for a little time, and some people said that depending on the detector, you could have a noisy that was related to the signal when the signal was interacting with the detector. So I don't know if it happens in this case.
Okay, so let's see. One thing you were asking, because I don't know if folks online could necessarily hear about it, you're asking about the effect of noise on these measurements.
Yeah, what kind of noises?
Right. Well, if there's a lot of noise, it's hard to measure any kind of correlation. I mean, if you're dominated by noise, that will reduce your signal to noise. Nevertheless, you can measure correlations. They're just reduced, and you need to integrate over more time. One thing you just mentioned was you can have noise that's caused by the signal. In that case, I must say it's not clear to me whether to call that noise or just signal distortion. That's kind of more of a detailed question. For example, you can have a photomultiplier tube which gives pulses even when there's no light coming, and that's called dark current. You can also have afterpulsing, where you generate a photoelectron, and that also generates another photoelectron from the cathode. That is related to the signal. I would call that signal distortion. It's kind of a technicality, but anything that's related to the light coming in and the intensity, I would call that signal, even if it's distorted. Any further discussion would be more technical, and we could talk offline. I'm happy to.
All right, thank you.
Okay, so any further questions? Otherwise, I'll be okay. So let me try.
So he said that he's ashamed to speak on microphone, but can yeah, so
You want me to-
have to explain to him how to do it.
Okay, so you would have to go to this page that I furnished before.
Maybe he could
Mute-
just type his question and you could tell it to me.
Yeah,
He did it.
yeah.
Yes.
Let me just
Yeah,
ask your
two
question here.
Two questions.
Okay, so the first question is the correlation function similar to the statistical correlation ratio in the sense of information we can get from the measured particle?
Okay, so
Similar.
is the correlation coefficient similar to the statistical ratio in the information content that we can get? I'm afraid I don't understand that question very well.
Yeah, me neither. I'm trying to understand the correlation ratio, statistical correlation ratio in the sense of information we can get from the measured part. Let me try the second. Maybe it will clarify the first.
Okay.
The information we can get from the hydrodynamic simulations with the correlation functions obtained from the Cooper-Frye formula must agree with the correlation functions which is obtained with the track count of final state particles in the collider.
Okay. So now you're talking about heavy ion collisions, and what you said is that the correlation functions that come from hydrodynamic calculations going through the Cooper-Frye formalism, which then turns the hydrodynamic system into particles, which then are usually correlated through the so-called Kuhn-Pratt formalism to make correlation functions. Yes, in principle, the proper comparison of theory to data is to do hydrodynamics, Cooper-Frye, Kuhn-Pratt, make a correlation function and compare that to the data. Yeah, that's the proper way to compare, yeah.
Okay, Isabella is trying to see if he can clarify that question.
Okay.
Well, meanwhile, any other questions? Let me see do they have questions here? If they do, you can raise your hand, please. I can open the microphone. Is there anybody wanting to ask questions? Okay, you just let us know if you do.
So I am here for a little while anyway, and anyone who has
So,
more questions, including the person online, we can talk later.
Okay, good. I have a question and
Yeah.
comment. The question is regarding your new experiment. So you're saying you can just record them and then just look into that the following day. But there is a time delay taken into account by the electronics, right? So in any case, because HBT is mainly the time difference. That's what you're measuring. So in a sense, they correlate knowing where they were and the arrival time, in a sense that they can correlate and take into account the time. Otherwise, you won't correlate your sources. Right?
Okay. So there's a time difference associated. So what Sandra was just saying is we're looking at time correlations. And ideally, or in some sense, we're looking for the probability for two photons to arrive. And you can already tell I hate this statement. They don't arrive. They happen. Nevertheless, we think of it that way. To arrive at the same time. First of all, there is an optical path delay. The wave travels further to get to this telescope. If the star is over this way, then it travels to get to that telescope. Nothing profound there, but nevertheless, it's true. So there's this optical path delay. You said something about electronic delay. Go
I
ahead.
mentioned that you somehow take that into account, even if you record that, but then the electronics or your software would match them or take into account the fact that they came from different paths, right?
That's what I showed here. So you're saying, do we take into account that they come from different paths? I mean, you can see that this optical path delay varies as a function of time. And we can calculate that exactly before we measure anything by knowing the position of the star. And yes, it lines up precisely, yeah.
Yeah, so you need the position of the star.
Is that?
Oh, yeah, you need to know where it is in the sky, just the angle. But we know where these stars are. I mean, there are these catalogs and Python libraries. I mean, I've learned so much astronomy, and I still don't know really any astronomy, but you don't need to know any astronomy. Python knows all the astronomy you ever want to know. And yes, you know where the star is, for sure. Yeah.
Now comes my comment. Can you go back to that beautiful slide where you see
My
Nicholas,
beautiful slide, they are all beautiful slides.
Bill Zeitz, Scott, and all the gang.
All right, I'm going to, here, talk into the microphone because I don't know if anyone can hear you. Okay.
Okay. So these are the guys in the late 86, more or less. I just wanted to know that because this was happening in another hemisphere, there was someone else also to contribute in there and studied the dependence on the average momentum of the pair and other stuff, and showed it hydrodynamically that there was a difference in time that would matter to take into account the behavior of the source, and we showed the momentum, the average momentum of the pair would have an interference. So this was shown by calculation. And more, interestingly, this is an assumption that protons can have hydro behavior. This was an assumption saying that you look into events with a large number of particles, and what you can do is you can describe this system hydrodynamically and look into HBT. So this was done as well.
It was also done by me in 2007.
Well, this was done in 1887.
Yes, I know. Yes, the claim was at Fermilab that, that even in PP bar, as a matter of fact, you can measure hydrodynamics.
This was used.
It was used. It was, we could talk about that experiment. I know very well about all about that
No, I was talking
experiment.
about a little girl theorist at the time.
A little girl, okay, I guess okay. I don't know about a little girl, but that would be interesting, yeah.
This was me, actually.
Okay,
I can give you the reference.
good, good. Oh yeah, I mean, there are many more people here, right? I mean, I'll just say, all of these, Shuriak, Galassi, Koonin, Pratt, Lednitsky, are all theorists, as a matter of fact. Bill Zeitz is just one of the most exceptional experimentalists that ever lived. He's still living. But there were tons of people besides this cast of characters that I put up here, just representative sample.
Of course, sure. Okay, any further questions, comments?
So Vinicius didn't type anything else. I don't know if he wanted to try to speak, but he didn't type
Yeah,
anything.
Let's have him talk to me
Yeah,
offline.
yeah,
That would be
yeah,
fine.
sure.
Okay,
Okay. So thank you so much. Any further questions, comments? So we can thank Mike again for the nice seminar. And thank all the audience outside and here for coming. Thank you. How do I? Oh, here end this, right?
Okay, so Vinicius, I think he's trying to talk.
Okay. Vinicius, você.
In the
Okay,
office,
okay. So Mike wants to talk to you later then. So let's close the meeting. Thank you very much. Ask him to contact you, and then we'll pass it to Mike. Thank you very much. I'll do or this guy does.
Eu faço, eu desligo.
Mas não é o cara lá que faz?
Eu acho que sim, eu vou chamar ele.